All right, my name is Tyler Clanton. My partner's name is Brian Custer, and we chose section 2.4. We're going to talk about partition matrices. So normally when we multiply two matrices, let's say we have matrix A and matrix B, then AB is just like the sum of the inputs. So AB plus BG, CE plus DG, AF plus BH, CF plus DH. So we're just doing row by column multiplication. But what if you had like a matrix that was 100 by 100 or 1,000 by 1,000, and you want to multiply them together? That'd be a lot of computations, and you don't want to do that. So to show a quicker way, what you can actually do is you can break the matrix up into different subsections. You can partition them into chunks. So let's say we have this matrix M, which is 4 by 4, and we want to solve for M squared. So we can take this original 4 by 4 matrix and we can break it up and partition it into sections. So if I break it up like this, now I have one section here. That's a 3 by 3 matrix. I have a section over here called B, C, and D. So this is a 3 by 1 and a 1 by 3 here. So then if we want to solve for M squared now, we can take this matrix that we've now changed into an ABCD matrix. So ABCD multiplied by itself. And so doing the same process as we do up here, where we go row by column, we get that this final matrix should be equal to A squared plus BC, AB plus BD, CA plus BC, and CD plus D squared. But the neat thing about whenever we partition it is, first of all, we can see that A here is just an identity matrix. So A equals I. And then the other important thing to point out is that the D is equal to 0. So if this D is equal to 0, we can immediately come over here and cancel out any term that has the, we can cancel out any term multiplied by D. So we can get rid of this DC here, we can get rid of this D squared, we can get rid of BD, and that's it. But what we can also do is anything that's A multiplied by A, which is the identity matrix, we can just write it as the matrix that it's multiplied by. So we know that AB is just going to equal B. We know that A squared is just the identity matrix squared, which we know that the identity matrix squared is still just the identity matrix. So that will just be A, or the identity matrix. And then we do have to solve for BC and CD. And also we know that CA is just C, because it's multiplied once again by the identity matrix. So if we want BC, we can just take this B section here, multiplied by our C section here. C section, get it? And so doing the same thing as we do up here, where we multiply row by column, we get 824, 412, and 1236 for our BC. And then our CB is the same thing. We take our C here, multiply by our B up here. And this is a good example of if we have a if we have a 1 by 3 matrix times a 3 by 1 matrix, we know that the resulting matrix should be 1 by 1. So that's why we just get one integer here. Same thing with up here in BC. We have a 3 by 1 matrix times a 1 by 3 matrix. So the resulting matrix is 3 by 3. So now we have all of our terms over here. We know that this first top section, this first 3 by 3 matrix that we're going to have here, is just going to be the identity matrix plus BC. So we can take our BC right here, which is 824, 412, 1236, and then we just add the identity matrix. So you're going to have basically just adding 1 to this diagonal here. So instead of 816 across that diagonal, you have 927. Everything else is the same. Then we have our B partition section right here, which was just equal to B, so it's just 213. We have our C partition section, which was just equal to C, so now we have 412. And then finally we have our CB, which is our D section, our D partition, which is 15. So this is the final resulting matrix of M squared, and obviously that's a lot faster than doing, what would it be, 16 different computations. So much quicker, and if you were to scale this up to 100 by 100 or 1,000 by 1,000, obviously it could save time if you could find certain ways to divide it up into different partition sections.
Okay, so we just got done having Tyler tell us a little bit about, giving us a little bit of a background in partitioning of matrices and giving us a little bit of a rundown, a reminder on how to actually multiply matrices. Now we're going to take that one step further. We're looking at Chapter 2, Lesson 4. We're going to Theorem 10, which is called column row expansion theory. And this is going to take a lot of those lessons of matrix multiplication and partitioning of matrices, and then we're going to sort of combine them together here. So here's what the theory says. If you've got two matrices, A and B, and matrix A is an M by N matrix, and matrix B is an N by P matrix, then AB multiplied together is going to be equal to the columns in row A multiplied by the rows of matrix B. And then you're just going to add those together. And so once you partition those matrices, which partition A into columns and B into rows, then this is the formula you follow, and boom, you get your answer. We got a proof down here. If that was confusing, honestly, the proof is probably going to be more confusing, but it'll make more sense once we run through the example. So I can read the proof quickly here. For each row index I and column index J, the ij entry in column K of A, row K of B, is the product of aik from column Ka and bkg from row Kb. Hence, the ij entry in the sum shown in equation 1 is ia bi plus, or b1, plus ai2, excuse me, b2j plus ain bnj. That's maybe a little bit confusing, but we're going to put it into practice right here. So take our example. Say you got two matrices, matrix A and matrix B. Matrix A in our case is a 2 by 2 matrix, 2 rows by 2 columns. Matrix B is 2 by 3. This is important because we're multiplying matrices. You have to remember that the columns of the first row have to match the rows of the second row. And that's true in partitioning as well. So make sure that matches up. We're going to partition matrix A into columns and matrix B into rows. That's what these dotted lines here are for. So A is going to be split into A1, which is a matrix 0, 4, and A2, which is -2 and -3. B is going to be split the same way, except in rows rather than columns. So 1, 4, 1, and -3, 0, and 2 are B1 and B2 respectively. So boom, now we got our rows, now we got columns, now we go back to our expansion theory and we multiply. We follow the rules, we can plug and play at this point. So we've got column 1A times row 1B, right here, A1 times B1 plus A2 times B2, a little bit of classic row multiplication here. We can follow a little squiggly line. And we got A1 times B1, drag the 0 across the rows. We got 0, 0, 0, over 4 times 1, 4 times 4, 4 times 1, 4, 16, and 4. Add that to the same calculation from A2 and B2, and you get 6, 0, -4, 9, 0, and -6. Add those together as per good old addition sign right there. Bada bing, bada boom. You just expanded out your matrix problem with column row expansion. Congratulations.